The Convair division of General Dynamics presents another in the series of audiovisual training programs on non-destructive testing. Liquid penetrant testing, a test method based on capillary action. Capillary action refers to the tendency of certain liquids to travel or climb when exposed to small openings. Insert a tube in a liquid and watch what happens. The liquid enters the tube and begins to climb. The speed and the amount of climb primarily depending on liquid viscosity, wetting ability, and surface tension. Liquid penetrant testing uses an oily liquid plus capillary action to detect discontinuities. The oily liquid containing a visible color or fluorescent dye is applied to the clean, dry surface of the test specimen and permitted to seek out possible discontinuities. After a sufficient time interval for the penetrant to enter discontinuities, dwell time, the surface film is removed. Often, a developer is applied. The developer, again through capillary action, acts as a blotter, drawing the liquid back to the surface. Visible color dyes produce high contrast indications in visible light. Fluorescent dye indications appear as bright glowing lines or spots under black light. Liquid penetrant testing is one of the basic non-destructive testing methods. It detects surface cracks, porosity, and through leaks in such metals as aluminum, magnesium, copper, brass, stainless steel, and titanium, as well as most alloys. Other materials can be tested, including ceramics, plastic, and glass. Liquid penetrant testing advantages are its simplicity and economy, its versatility. It provides direct indications. The method is sensitive to very fine openings. Limitations are discontinuities must be open to the surface and free of contaminants. Penetrants must be able to enter discontinuities. Because the penetrant response from porous surfaces can mask discontinuities, it is difficult to test porous specimens. And some penetrant materials can harm test specimens. Special penetrants must be used. Different liquid penetrant processes are identified by the type penetrant used. The most versatile but least sensitive are the color contrast or visible dye penetrants. The dye, usually a bright red, is sometimes a special color, such as blue. The chief limitation is a marginal ability to provide enough contrast to detect fine openings. For greatest sensitivity or seeability, fluorescent penetrants are used. They contain dyes that fluoresce when exposed to black light. The penetrant color is usually green. The fluorescence, a bright yellowish green. For special applications, there are fluorescent penetrants that glow red or blue. Dual sensitivity penetrants contain a combination of visible color and fluorescent dyes. The visible color is generally a bright red. The fluorescent color, a yellow to orange red. Examinations are made under visible light, and questionable indications are resolved with black light. Methods of penetrant application include dipping or immersing the test specimen in the penetrant, spraying with a gun or aerosol can, flushing or pouring the penetrant over the specimen, or applying the penetrant with a brush. Liquid penetrant processes are further classified as to the method of penetrant removal. The water-washable method employs penetrants containing an emulsifying agent. Excess penetrant is removed by washing with water. The best wash being a forceful spray of large water droplets. The post-emulsified method is a two-step removal process. The penetrants do not contain an emulsifying agent. They require a separate emulsifier to make them water washable. The emulsifier, usually dyed orange to contrast with penetrant, may be either lipophilic, an oil base, or hydrophilic, a detergent water base. Lipophilic emulsifiers begin emulsifying on contact. They are applied by spraying, flowing the emulsifier over the specimen, or immersing the specimen in the emulsifier. Immersion being preferred because the emulsification is more easily controlled. On application, the emulsifier starts to work at the penetrant interface, diffusing into the penetrant, making it water washable. Diffusion stops when water is applied. The emulsifier is washed from the test surface, carrying the emulsified penetrant with it. Hydrophilic, water-based emulsifiers can also be used as contact emulsifiers. But more often, the emulsifier is diluted and sprayed under pressure. It acts as a low-energy scrubber in removing excess penetrant. The washing action stops when the spray is stopped. Solvent-removable penetrants are post-emulsification penetrants. But instead of using an emulsifier and a water wash, excess penetrant is removed by a solvent. Solvent removers include commercial solvents such as naphtha and mineral spirits, in addition to special formula proprietary removers. Excess penetrant is removed by washing with a clean cloth or towel moistened with remover. Developers are used to blot or absorb penetrant, to magnify indications, to create a high visual contrast between indications and surrounding area. Different developers are water-suspended particle, water-soluble, dry powder, and non-aqueous suspended particle. Water-suspended developers are the least sensitive. The developer is suspended in water and must be continuously agitated to prevent settling. Developer is applied by immersion, or flowing the developer over the specimen, and then allowing the developer to dry, leaving a white powdery film that absorbs penetrant. A higher level of sensitivity is obtained with water-soluble developers. The developer is dissolved in water. Application is by dipping, pouring, or spraying. Dry powder developers have about the same sensitivity as water-soluble developers, the developer being a fluffy, chalk-like powder. Application is by powder gun, squeeze bulb, or soft brush, or by using powder-filled dip tanks or dust chambers. Best sensitivity is obtained with non-aqueous wet developers. The developer is suspended in a solvent. Evaporation of the solvent helps draw penetrant from discontinuities. Non-aqueous developers are applied with spray cans and conventional sprayers. In addition to the conventional penetrants, removers, and developers, special materials are available. Low sulfur and chlorine materials for testing certain nickel alloys, stainless steels, and titanium. There are special purpose inert penetrant materials for testing specimens that come in contact with liquid oxygen, and rubber, plastic, and food compatible penetrant materials. High temperature penetrants for testing hot welds, special penetrants for testing at low temperatures. Supersensitive penetrants for detecting extremely fine discontinuities. Penetrants that provide excellent contrast and sensitivity without a developer. And special wax and plastic film developers that absorb and fix penetrant indications provide permanent records. Recording of penetrant indications is sometimes done using a strippable lacquer. Several layers of lacquer are applied over the indication and allowed to dry. The coating is then lifted, bringing the indication with it. Another method is to spray the indication with a fixer, and when dry, lift the indication with transparent tape. The tape then being transferred to the appropriate test document. Photographs are excellent in recording indications, both black and white and color, with Polaroid film providing the ultimate inconvenience. There are two basic types of penetrant test equipment, the portable kit and the stationary or tank system. This is a visible dye kit. It consists of a carrying case, solvent cleaner or remover, red dye penetrant, and a non-aqueous wet developer. The kit includes wiping cloths, a brush, and operating instructions. Materials are easy to apply, and they produce high contrast indications in visible light. The fluorescent kit is similar, except a fluorescent penetrant is provided, and it includes a black light. The light consists of a current regulating transformer, lamp housing, mercury vapor arc bulb, and a deep red-purple filter. What is black light? It is light radiation in the near ultraviolet range of wavelengths between 3,200 and 4,000 angstroms. Though it is invisible, black light causes many materials to visibly fluoresce or glow. Best sensitivity to fluorescence is obtained in a darkened area. Stationary systems range from the simple to fully automatic electrostatic systems designed for specific applications. The number of stations and their arrangement is governed by the penetrant used, the penetrant process or method of removal, and the type of developer. The typical post-emulsification system has, in order of use, a penetrant tank, a drain station, an emulsifier station, and a rinse station. Fluorescent systems include an overhead black light to aid in rinsing specimens. This setup shows a wet developer tank next, followed by an oven dryer. When dry developer is used, the two stations are switched. The dryer is located next to the rinse station. Next comes a conveyor or rest station, followed by an inspection booth. Depending on the type of penetrant, black light and/or visible lighting is provided in the booth. Water washable systems have the same arrangement, except the emulsifier station is omitted. Rinse stations often include a handheld sprayer to aid washing. Many also have a pressure-regulated air gun to facilitate water removal. Emulsifier stations frequently contain spray nozzles to facilitate emulsifier application and, in the case of hydrophilic scrubbers, to remove excess penetrant. Wet developer tanks include pumps to agitate the developer and prevent particles from settling. Dry developer stations almost always have a dust collecting system. Preferred drying ovens are electrically heated and use recirculating hot air. Auxiliary equipment includes handheld sprayers and applicators, timers to monitor penetrant and emulsifier dwell times and to control drying times, thermostats and thermometers to control temperature of penetrant materials and drying ovens, exhaust fans to remove fumes and dust, and hydrometers to measure the specific gravity of wet developers. And many systems have pre-cleaning and post-cleaning stations to prepare specimens for test and to remove penetrant materials after test. More about cleaning, test procedures, and interpretation of indications in Part 2. Liquid penetrant testing detects only discontinuities open to the surface. To find subsurface discontinuities, another method of testing, such as ultrasonic testing or radiography, must be employed. Porous materials can limit liquid penetrant testing, making it necessary to select another method. Again, only discontinuities that are open to the surface are detectable with liquid penetrant testing. The penetrant and processing used depends on discontinuities sought and material being tested, the test specimen. Factors to consider are sensitivity, specimen size and shape, number of specimens being tested, and available equipment and facilities. Sensitivity refers to the ease and certainty of small amounts of penetrant being seen. Required sensitivity is being able to locate discontinuities of a particular type in a particular specimen. Coarse surface defects in a rough casting, or fine cracks in some exotic material, such as the boron aluminum tubing in a space vehicle. Color contrast and fluorescent penetrants have about the same penetration ability. Either may be used in locating large discontinuities. The primary limitation of color contrast penetrants is getting enough contrast, enough penetrant into a discontinuity to form an indication. To gain contrast, a heavy concentration of dye is used, plus developers that provide a flat white background. Maximum contrast, seeability, is obtained with fluorescent penetrants. Their brilliant glow catches the eye and magnifies. Simplicity and portability are advantages of color contrast penetrants. Kits contain all that is needed in performing spot checks and tests in the field. Materials are sprayed on and wiped off. No electrical power is required. Neither is a darkened area. Slightly less versatile is the fluorescent penetrant kit, but it provides better sensitivity in locating fine cracks. Stationary or tank systems are for production testing, particularly when there are large numbers of parts. Usually, fluorescent penetrant is used. Penetrant materials and test specimens must be compatible. Sulfur and chlorine adversely affect certain nickel alloys, stainless steel, and titanium. Testing requires penetrant materials low in sulfur and chlorine. Only liquid oxygen-approved materials shall be used in testing specimens that come in contact with liquid oxygen. Plastic and rubber are sometimes attacked by penetrant materials. When in doubt, tests should be performed first on a piece of scrap. Retests, when required, should be performed with the same type penetrant. Switching from color contrast to fluorescent or vice versa is not recommended. When two levels of sensitivity are required, a dual sensitivity penetrant should be used. Gross discontinuities may then be located under visible light, and examinations for fine cracks, porosity, and penetrant residue carried out under black light. The three basic penetrant processes are water washable, post-emulsified, and solvent removed. The water washable method is used for high production testing of small parts or testing rough surfaces, threads, or keyways. A disadvantage is that conventional penetrants are easily washed from shallow discontinuities. Use of gel-forming or slow solubility penetrants minimizes this wash-away problem. The post-emulsified method adapts readily to high production testing, especially of large specimens. Emulsification, and therefore penetrant removal, is more easily controlled. There is less danger of washing penetrant from shallow cracks. Use of low-energy emulsifiers or hydrophilic scrubbers further improves sensitivity. The solvent-removed method is usually used for spot checks or tests in the field. Because solvent-removed penetrants are quickly washed from discontinuities, care must be taken to avoid overwashing. Use of an inhibited solvent remover slows down washing and improves reliability. Developer selection depends on available equipment, specimen surface condition, and required sensitivity. Wet developers, water-suspended particle and water-soluble, are most effective when applied to smooth surfaces. Greatest sensitivity is obtained when applied as a spray. Dry developers are more adaptable to rough surfaces and automatic processing. They're also the easiest to remove. Non-aqueous wet developers are used mostly for in-field testing and spot checks, and when greatest sensitivity is required. Controlling specifications and standards decide material and equipment requirements. They also establish required sensitivity. In performing liquid penetrant tests, we must be aware of possible health hazards and safety precautions. Continual exposure to penetrant materials can be injurious. Fumes can create a fire hazard. Splashing of materials on clothing should be avoided. Oil-resistant gloves and aprons should be worn. And face and eyes should be protected by wearing a face shield. Tests should not be performed near spark-emitting equipment, nor open flames. Blacklight itself is safe, but the mercury arc bulbs used also emit harmful ultraviolet rays. Never operate blacklights with missing, cracked, or broken filters. Liquid penetrant test procedures involve 6 basic steps: surface preparation, or pre-cleaning of specimen, penetrant application, excess penetrant removal, developer application, inspection, and post-cleaning, the removal of penetrant materials from test surfaces following test. The single most common cause of failure is poor surface preparation. Contaminants can seal off discontinuities, trap penetrant, cause non-relevant indications, obscure true discontinuities. Surface preparation begins with removal of foreign materials such as paint, loose dirt, scale, and rust. Mechanical cleaning such as wire brushing or abrasive blasting should be limited to occasions when no other cleaning method will suffice. Use of such methods may smear or peen test surfaces and fill discontinuities. Chemical cleaning and paint removal is preferred. Methods of application range from simple brush-on or wipe-on and wipe-off techniques to immersing specimens in solutions. Vapor degreasing, when it doesn't harm specimens, is especially effective in removing oily films and grease. The resultant heating helps drive off and evaporate moisture in discontinuities. Detergent cleaning is best for removing inorganic or solid soils. However, solutions used must be non-corrosive to specimens being cleaned, and following cleaning, a thorough rinsing and drying is necessary. Methods of expediting drying include the use of hot air blowers, heat lamps, and ovens. Other cleaning methods include ultrasonic and steam cleaning. Steam cleaning being particularly useful in cleaning large, unwieldy specimens. Chemical etching, when approved, is often desirable following mechanical cleaning. It's useful in reopening discontinuities closed by machining or grinding. Whatever the cleaning method, it must not harm the test specimen. It must leave test surfaces and discontinuities dry and contaminant-free. Methods of penetrant application include flushing, spraying, brushing, and dipping. A uniform film of penetrant is applied and allowed to seek out and enter discontinuities. When tanks are used, the specimen is immersed in penetrant, raised, and allowed to drain. The duration, dwell time, wet penetrant must remain on test surfaces, depends on the discontinuities sought and temperature. Tight cracks require a longer dwell than open cracks. Low temperatures increase the dwell required. Heating may assist in opening discontinuities and shortening dwell times, but the practice generally is not recommended. Best sensitivity and reliability is obtained with penetrant and specimen temperatures between 60 and 125 degrees Fahrenheit. And in most instances, a dwell of 5 to 30 minutes is sufficient. Longer dwells requiring the rewetting of test surfaces. Rewetting also makes removal of dry penetrant easier. Removal of excess penetrant depends on whether the penetrant is water washable or post-emulsified. Water washable penetrants are best removed with a spray of large water droplets and a water temperature between 60 and 110 degrees Fahrenheit. Water pressure should be 30 to 40 pounds per square inch, and the nozzle directed at about 45 degrees. The wash should only be long enough to remove excess penetrant. Fluorescent penetrant removal is accomplished with the aid of black light. Rinsing is stopped when surface fluorescence disappears. Removal of post-emulsified penetrants begins with application of emulsifier. Best control is obtained by dipping. Brushing or wiping is not recommended. Emulsifier, on application, immediately begins diffusing into the penetrant. Action stops when water is applied. The duration or length of emulsification is critical. Too little time and surface penetrant may not be completely removed. Too much time and the penetrant in discontinuities becomes water washable. Emulsification time used depends on the specimen's surface condition and the type discontinuities sought. Average times range from 1 to 3 minutes, seldom exceed 5 minutes. Correct time is determined by experiment. The pre-cleaning, penetrant application, and removal steps are repeated using different emulsification times until desired wash is obtained. Using hydrophilic scrubbers, post-emulsified penetrants are emulsified and removed in the same manner as water washable penetrants. Washing action stops when spray is stopped. Using solvent removers, penetrant is usually removed by first wiping with a clean, lint-free towel, then following with another towel slightly moistened with remover. Solvent should not be applied directly to the specimen. Next comes developer application. Water-based developers are applied immediately following the rinse. Dry and non-aqueous wet developers are applied only after the specimen is dried. Best results are obtained with a thin and even coating. No pools of wet developer or accumulations of powder. Thickness of water-based developers is controlled by bath strength. Specific gravity is measured with a hydrometer and developer or water added as needed. The specimen, on removal from the bath, is positioned so that fillets and recesses can drain. Depending on specimen thickness, the drying temperature used for most applications is between 150 and 225 degrees Fahrenheit. Drying time should be just long enough to dry test surfaces. When using dry powder developers, the specimen is dipped or dusted and the excess powder removed by gently blowing, shaking, or tapping. With non-aqueous wet developers, best results are obtained with a light and even spray that doesn't soak the test surface. Developing time also is important. It must be long enough for indications to develop, but not so long that they become blurred or distorted. Using water-based developers, the time in the drying oven is usually sufficient. Using dry or non-aqueous wet developers, the accepted norm is 7 to 30 minutes. Next comes inspection, the searching out of penetrant indications and determining their cause. Cracks, cold shuts, seams, and forging laps show up as continuous line indications. The same discontinuities may appear as intermittent or broken lines, the discontinuity being partially closed at the surface. Small dots and rounded indications generally indicate porosity, small inclusions, or blowholes. Indication size, intensity, and amount of bleeding provide a rough estimate of discontinuity size. Fine cracks and porosity produce faint indications. The wider or deeper the crack, or the larger the porosity, the larger and brighter or more rapidly spreading the indications. There are also conditions that produce false or non-relevant indications. Poor or incomplete washing of penetrant from test surfaces is probably the most common cause. In this example, the resultant streaks and patches of fluorescence could mask possible discontinuities. Rough surfaces, sharp fillets, and blind holes can retain penetrant, causing non-relevant indications. Lint and dirt produce indications similar to discontinuities. Other sources of non-relevant indications include threads, keyways, and press fits or joints. This magnesium casting shows a number of visible dye indications. The red spots and splotches indicate surface porosity and possible micro-shrinkage. Several large cracks are visible at bolt holes. We know they are large by the amount the penetrant has spread. Another view of the casting. Indications at bolts are typical of non-relevant indications resulting from assembled parts. This particular example shows the outline of an inclusion. Non-relevant indications appear in threads and at lockwire hole. Here we have a cracked weld. The intermittent red line is the crack. Crater cracks may appear as rounded indications. These specimens show several small fatigue cracks. Also notice the non-relevant indication at the rivet in the specimen on the left. This is typical of indications caused by press fits and joints. The danger in this indication is that it may conceal true discontinuities. When in doubt, specimens should be retested and indications watched as they develop. Discontinuities may be the result of faulty manufacturing or processing. Fluorescent penetrant has revealed several blowholes in this aluminum casting. Random porosity is also evidenced. Laps and a small radius crack are visible in aluminum die forging. This weldment shows excessive porosity in both the parent metal and the weld. A hairline crack appears at the edge of the weld. Other sources of indications may be cracks caused by improper heat treating, machining, and grinding. Indications appearing on this aluminum angle are tears resulting from stretch forming. Our final example is this machined steel fitting. The crack indications are typical of indications occurring at points of high stress. Because penetrant and developer residue attracts moisture and may cause corrosion or may interfere with subsequent processing or usage, the final step in liquid penetrant testing should be a thorough post-cleaning. Methods employed are the same as those recommended for pre-cleaning. Detergent cleaners produce the best results in removing water-based materials. Vapor degreasers are best in removing oil-based materials. In conclusion, the reliability and effectiveness of liquid penetrant testing depends on our knowledge of the penetrant processes and the thoroughness with which we conduct tests. Experience. It requires familiarity with manufacturing processes, knowledge of discontinuities likely to occur, and appearance. Knowledge of how different materials fail and where. Only then can determinations be made of specific